seems to work. So very nice to see you again. Okay, it's been 2 weeks. Today we'll finally get to something really non-trivial. So we're gonna today we will be able to talk about how to sample from the result of an acyclic join. Okay, so um, this is uh, something that has a lot of applications. Um, so we will talk about some of them later. Okay. First of all, let me help you review the most important concepts that we talked about before. Instead of going through the formalization again, which is boring, I like to start with an example. Okay, whenever necessary, I'm going to insert um, the formalization. But so I will be aware that we have already talked about all those formalizations. Um, so I'll try to make the discussion as interesting as possible. Okay. Well, let me start by showing you an acyclic join. So I'm showing you a join tree. I hope this makes sense to you because if it does not, and then there are a lot of things I have to talk about. Um, so here you see a tree. Um, so you so there are four nodes in the tree, right? So if you look at this um, BG, right? So what does that mean? So this means it indicates a relation, right? So the relation has two attributes, B and G. Okay. Um, So we have how many relations here? We have one, two, three, four, five, six. Okay, six of them. Okay. Um, we have six relations, and you can see I drew the tree in the form of a rooted tree. Okay, so this is intended. Okay, so when I say a joint tree, this is something that you can definitely find for an acyclic query. So when I say joint tree, normally it's not a rooted tree. But for today's discussion, in general, right, whenever you talk about Yanakaki's algorithm, and then you always talk about a rooted joint tree. All right. So BG, the node BG here is the root of the joint tree. And I can say something like BE, this is a child of BG, right? So that will make sense. Now, another thing that's going to be mentioned again and again is the subtree. Okay, subtree. Now, this time, this subtree is a rooted subtree. All right. So, for example, if I say, look at this internal node, BE. All right. So, what is the subtree of BE? Okay, subtree of BE, and then this is the um, triangle part here. Okay, so that is the subtree. And what if I say the subtree of AB? All right, what does that mean? Well, it means it contains only a single node. All right, so this is the idea. Okay. Now, formally, in general, if you have a join, um, in my presentations so far, I have defined a join as a set of relations, right? Because already once the relations are fixed, and then the join result is also fixed, right? So here I have six relations, okay? So in general, if this join Q is defined, and then I have a graph defined, right? So this graph is, um, denoted as this, and I hope you still remember. So this V includes all the attributes. Okay, so for example, here it will be A, B, C all the way to H, F, G, H, H. Yes. Okay. And what about this set E there? Right. This is set E. This is a set of schemas. Okay, relation schemas. Right. Oftentimes we use the term hyperedge to refer to it, right? So here, this is one edge, BG, and this is another edge, right? Just for simplicity, I don't really have hyperedges here because I don't think this is the point today, right? You already understand what that means, okay? You also have to understand that all the relation schemas appear in this join tree. Okay, in general, this is a join tree of the schema graph G. Okay, good. Um, I'll typically use small e to refer to a hyperedge um, in the schema graph. Okay, so this small e here could denote BG, for example, right? So if I say ye, that's a hyperedge, right? And that's a no, it also makes sense, right? Because once again, there is a one-one correspondence between the nodes in this John tree and the hyperedges in the graph, right? So if I say ye, and then it corresponds to a no in the John tree, right? And that allows me to say something like R subscript E, right? So for example, if I say, okay, what is RBG? And then this is the relation corresponding to the root of the John tree. Okay, good. So here we have 6 relations, and you want to compute a join, right? A join would like to compute the joint result, all right? So this is something we can already do using Yanakaki's algorithm, right? But today we're going to achieve 2 purposes. The first purpose is that we don't want to compute the full joint result because that's going to take a lot of time, okay? I'm going to talk about that in a little bit, okay? But there are 2 things we want to be able to do. The first thing is we just want to know how many results there are in the joint result. Okay, how many tuples there are in the joint result. Okay, and the second thing is we'd like to build a data structure such that whenever you want, you can uniformly sample from the joint result as if it had been computed, right? As if, of course, you don't want to compute it, right? So here comes the question, right? So you can see both purposes can be easily achieved if you just go ahead and compute the joint result. Okay, why don't you want to do it? Okay, why don't you want to do it, right? Um, by the way, for today's discussion, for simplicity, we will assume that this G has a constant size. Okay, constant size. So this basically means that the number of attributes that you have is a constant, and also the number of the number of relations you have is also a constant. All right, so this V here has a constant size, and this E here, this big E, right, also has a constant size. Okay, so this is known as the data complexity, right? So we will be measuring the problem size as the number of tuples rather than the number of attributes, right? So this is also the typical case you will encounter in practice. Okay, so going back to my earlier question, okay, my earlier question requires this. Um, uh, you know, the answer to my question, requires this constant size assumption. So my question was, for the purpose of counting the joint result size and also sampling from the joint result, right? For these 2 problems, one straightforward approach is simply just go ahead and apply Yanakaki's algorithm to compute the entire joint result, right? So once the result is there, you know how many tuples you have generated. And second, you can store the entire joint result in an array, right? In an array. So every time you want to sample from it, you just sample from it, okay, in constant time, right? So why don't we want to do this? Okay, so this is the first question I want to answer, all right? Otherwise, there's no point continuing, right? If this was feasible, and then there's no point continuing, okay? So the answer to this question is that the joint result can be gigantic. Okay, the joint result can be gigantic, right? Not all of you are able to see this yet. However, I can tell you that the joint result, this joint might have n to the power of 4 where this n is the total number of tuples in the input relations, okay? I can tell you this is not trivial. Okay, this has something to do with the so-called AGM band, which we'll talk about, several seminars down the road. Um, so I can tell you that this result, the joint result, can contain up to n to the power of 4 tuples. Okay, n to the power of 4. All right. So, well, if you want, yes, if you don't mind spending n to the power of 4 time, and then indeed you are able to achieve both purposes, using the brute force approach, right? However, today, our goal is to do much, much better. Okay, our goal is to achieve big O in time. Okay, rather than n. N is not entirely clear here. Okay, I would say in. Okay, in is the input size. Okay. By the way, since I have already assumed that the schema graph has a constant size, I don't really have to say, okay, in is the number of integer values in the input relations. Okay, because every tuple has a constant number of values, right? I can simply say in is the number of tuples, right? So they are asymptotically the same, right? So that actually makes it conceptually cleaner. Okay, so today we want to achieve two purposes. Okay, the first purpose is that we want to be able to compute the number of tuples in the joint result in just linear time. This is absolutely the best you can do, right? So you have to scale all the tuples at least once for that purpose, right? So what if I say, hey, once you have spent this much time, you actually get the entire, I'm sorry, you don't get the entire joint result, but you get the size of the joint result, right? So that's one cool thing, right? So another cool thing is that, oh, by the way, when I say in, I should have mentioned this tilde O there, which means, I don't care about polylog factors, right? Why? Well, that's basically because I don't want to spend another hour talking about the gory details, right? Once you understand the main ideas, and then it becomes an implementation problem, right? You can actually remove all the polylog factors by resorting to hashing. But today, I will not spend too much time on such kind of tedious details, right? So that is the first purpose we'll achieve. Another purpose we'll achieve is, we will build a data structure in how much time? Also, this much time. Okay, so basically the linear time, and the data structure has a linear size. Okay, so big O of in. All right, no tilde. Okay, big O of in. So this is pretty much as the space, right? Pretty much as the space needed just to store the input relations, right? You cannot, asymptotically speaking, you cannot do better than that. But it gives you something extremely powerful. Whenever you say, I want a random tuple from the joint result, you just go to this structure, all right? So the structure will be able to return you a uniform sample in constant time. Okay, so that is um, that is today's purpose. Okay. All right. Good. So I can see you are ready for this. So now let's just get to it. Okay. Let's get to it. Okay. Well, some fundamental lemmas, which I have talked about in the previous seminars. The first one is fully reduced. So I will be talking about only fully reduced acyclic joints. Okay, I hope that makes sense to you. Okay, so essentially this means that every tuple here in these 6 relations is necessary. Okay, necessary. Now, what do I mean by necessary? This is the point where the concept of fully reduced, right, comes in, right? So intuitively, if a tuple is useless, which means it's dangling, right? It's dangling if after removing the tuple, the joint result doesn't change, right? So this means the tuple is not going to affect anything, right? So um, we could have removed the tuple and just saved us some time, right? So we assume that we do not have such kind of dangling tuples, right? So if you don't have such kind of tuples, and then we say that the input joint is fully reduced. okay? Because all the relations have been shrunk to the minimum, right? So why is it fair to make this assumption? Well, it's fair because we have already learned that I can give you an arbitrary acyclic join, right? And you are able to remove all the dangling tuples in just linear time. Okay, well, we're talking about constant size, constant schema graph here. We're talking about data complexity, right? So I proved a lemma before. Okay, so this is the first thing we want to understand. Okay. Now, another thing that we need to understand is this decomposability, because you won't be able to talk about how to solve those two problems unless you understand this decomposability, which reveals a very important structure on the joint result. Okay. And also, this decomposability is a unique feature of acyclic joints. Okay. So basically, this is the property that is leveraged by Yanakaki's algorithm. Okay. So this is actually the property that separates acyclic joints from, cyclic joints, acyclic and cyclic. Okay. So this is the property that really creates all the differences. Okay. Acyclic joints, such as this one here, has this property. And this property essentially says you are able to decompose the computation into the subtrees. Okay. So let's understand what it means here. Okay. So this is going to take um, um, a few minutes. Okay. Because this is very, very important. Okay. Now, think about the root here. Okay, I will start from the root. Okay, so think about this root, and if I say RBG, that makes sense to you, right? RBG. Okay, RBG is the relation at the root, right? Good. Okay. Now, I'm going to. I will need this later. All right. Now let's look at the joint result Q. Q here, so Q here is the join that you are seeing here, the join with 6 relations, okay? So if I say, okay, join Q, so that means this is the join result I want to compute, right? So a very quick question. So this join Q is a relation, right? Because the join result is a relation. How many attributes are there in this relation? Well, you should tell me A, B, C, D, E, F, G, H. Okay, I lost count, but those are the attributes, all right? So indeed, this John Q is the final result, okay? Now, clearly, this is, so if I look at every tuple, so this is RBG, okay? RBG, all right? So if I look at every tuple in this RBG, by the way, we have a relation, and a relation cannot contain duplicate tuples. All right, so this is something very important. All right, a relation is defined as a set of tuples. Okay, and therefore, if you have two tuples in this relation BG, these two tuples they differ either in their B values or their G values or both. Okay, otherwise they would be duplicate tuples, right? Which is not allowed. All right. So if you look at every single tuple and then you say, okay, you know what? I take out this tuple and join this tuple together with the other 5 relations. You see what I'm saying? And then you will be getting such a join. You see what I mean? So you have RBE, joins RAB, joins RBD, and then joins REF, and then joins RGH. You see what I'm saying? So it's essentially like, okay, I have this RBG there, right? But I instead of looking at this RBG as a whole, I say, okay, you know what? I'm going to look at every tuple inside the RBG individually. Okay, so I look at this tuple and then I join this tuple together with the other 5 relations to see what I get, right? And then that itself is a join result, right? That itself is a join. You see what I'm saying? Because you can imagine that, in the first relation, it's so small that it contains only a single tuple, correct? Okay, so that's what you do here, okay? And now if you put together all the results of all these joins, you see what I mean? So you look at every single tuple, all right? You put together all those individual joins, and then you put together their results, and then you get the final result. You see what I'm saying? Now, this is something. This is not decomposability, by the way. I'm going to get to decomposability very shortly. However, this itself is kind of important because this tells you that if you want to get the entire joint result, what you can do is you take a relation out, and then you look at every single tuple individually, right? So you look at this tuple, and then you join it together with the other relations, and then you get a result, and then you put together all these results, and the union. Actually, these two results are mutually disjoint, right? Because the tuple U itself is different, right? So you don't really have any result tuple reported twice. Okay, so this is very important for today. Okay, very important for today. Good. Now let's get to the decomposability part. All right. So now let's focus on this. All right. Decomposability is about this small joint, this individual joint. All right. Why did I say individual? Because I'm talking about an individual tuple here, U. Okay. So decomposability says, you know what? For on this expression, there is a Cartesian product behind it. This is what decomposability is saying. All right. Now let's look at this. Right. So let's look at this red expression. Okay. So I want you to imagine, there's a U here, U in the relation BG, correct? And this U, let's say, has small b and small g as the values. Okay. So you can join this UBG with, these two parts separately. You see what I'm saying? Okay, so let's do exactly that, right? So if you look at the left triangle, and then you get um, a join between you and how many relations? 4 relations. You get AB, you get BD, you get EF. All right, so this is, as you can see, this is joining you with the left triangle, okay? And then you say, you know what? You will be taking the Cartesian product. Okay, you'll be taking the Cartesian product with the other side. Okay, by the way, this is Cartesian product. Now pay attention to it, all right? So you'll be joining on the other side. On the other side has only one relation, right? Okay. Well, this Cartesian product is a very bold claim. It's a very courageous claim, okay? Because it says, I'm not going to check anything else. You take a tuple from the left-hand side, you take a tuple from the right-hand side blindly, okay? I don't care which tuples you have grabbed. You put them together, you definitely get a result here, result in the individual joint, okay? So this is the decomposability, okay? So you have this only for acyclic joints, all right? So this decomposability lemma is something we proved in 2 weeks ago. Okay, so that was basically the main weapon. Okay, all right. Now the thing is, this decomposability holds everywhere. You see what I'm saying? So here I'm talking about BG, right? But you could say, all right, so now let's look at this BE and let's put a tuple there, okay? And you can consider this John tuple inside this triangle. You know what? Let's make it precise, right? So let's look at this U. So U is a tuple inside RBE. Okay. So if you look at the left subjoin, right? So I'm interested in saying, okay, what is R? What is the join between U and then AB, and then BD, and then EF. Okay. So now remember, this tuple U is in BE this time. Okay. So by decomposability, immediately you can say, okay, in my eyes, this is just a Cartesian product. Okay, you can compute 3 joints separately, and then you do the Cartesian product. Okay, no more checking. Okay, the Cartesian product, all the tuples there will be reported. Okay, so that's exactly the idea. So more specifically, as I said, right, you simply do 3 joints. U joining R, B, D, U joining R, E, F, okay, and these three joints, and then across them you do Cartesian product. Okay, so this is um, um, uh, so this Cartesian anyway. So I should say so some projection, because when you do Cartesian product, this is very very pedantic. If I want to be fully correct, I should be aware that the attribute E, right? The attribute E will appear three times. Anyway, so you see what I mean? Okay. Um, so maybe I should say, this is essentially identical. Okay, so if you see what I mean. So, okay, good. So this is the decomposability fact. All right, good. Now, this is important. All right, so I want you to remember this for today's discussion. Okay, good. Well, before I can talk about counting, I'll first talk about counting and then sampling, right? Before I talk about these two problems, I would like to first um, bring out two preliminary structures, okay? Because I will have to build some data structures on the fly, okay, as I go on the fly, so that I can utilize these data structures to help myself do the computation. Okay, so the first one is what I would like to call group by sum. Okay, so so let's say I have a relation AB. Okay, let's say AB. Okay, so let me give you the acyclic joint. Okay, so this is the acyclic joint from the previous page. All right, so let's look at this relation AB. Right, so this relation AB. There were two attributes. Right, so I will show B first. Two attributes. Now I would like you to imagine a group by operation. Okay, a group by. I would like you to group the relation by B. You understand what that means, right? So essentially, you're saying if two tuples they have the same B value, and then they are added to the same group. Okay, or if you want equivalence class, doesn't really matter, right? Same group. All right. So you could have as many groups as the number of distinct B values in this relation. You see what I'm saying? Okay, good. Well, also imagine that every tuple is associated with an integer weight. Okay, so this weight is something greater than 0. Okay, so this is not really a column of the table, right? But for this group by sum problem, right? You can imagine that in addition to A and B, you have also a weight associated with every single tuple, right? And this weight is an integer. Okay, good. Now I can talk about what is group by sum. A group by sum essentially saying I'm giving you a B value. Okay, let's say a B value that corresponds to this group. Now remember, all the tuples in this group, they share the same B value, correct? Okay, so I would say, okay, I want that group. Okay, but I don't want the tuples. You see what I'm saying? I want only the sum of the weights of those tuples. You see what I'm saying? Okay, so basically I'm saying, okay, give me the sum of the weights of these three tuples here. Okay, so this is what I would like you to do. Okay, I hope this is easy because it is. Okay, you can, for example, you can simply pre-compute the weight sum for every group and just store it there, right? Anyway, so you are able to do linear space. Linear space here basically means, a space that is proportional to the number of tuples in the relation. Okay, so this is the amount of space, and you can do okay. You know what? Here I will expose the factor. You can build the data structure in so much time. All right. So basically, just sorting. Right. And whenever I want a group by sum, okay, I name a group. I say, okay, find me the total weight of the tuples in the group, and then you can give it to me in basically log n time. Okay, so this is possible, right? So this is something very easy, correct? Good. Now, this is the first data structure we'll need today. Okay. Now, another data structure we will need. By the way, this is for counting the result size. Okay, and the next data structure we will need is called group by weighted sampling. Weighted sampling. Okay, weighted sampling. All right, so what does it mean here? Well, it means the following. Look, again, I'm going to name a group just like this. Okay, I will name a group. Now, this time, I want to sample from the group. Is what I'm saying. So here I have three tuples there, right? So I want to sample from those three tuples. However, this is not uniform sampling. This is not uniform sampling. Okay, so this is weighted sampling. You see what I'm saying? So for example, if I say W1, W2, and W3, so these are the weights of those three tuples, right? I want to sample every tuple with a probability proportional to its weight within the group. You see what I'm saying? And therefore, if you say, okay, there were three tuples here, so this is, let's say, U1, U2, and U3. These are three tuples, right? And it's essentially what I want is, I want a random variable X, right? Because this is sampling, right? So this is the output is random, random output. So the probability for X to be UI, okay, as I said, right, it should be proportional to its weight. But what does that mean exactly? The meaning is Wi over W1 plus W2 plus W3. Okay, good. So again, I'm not going to explain the details, but you are able to create a data structure meeting all these requirements. So by the way, this is for construction, and this is for query. Okay, so you are able to build a data structure meeting all these requirements. Okay, linear space. If n denotes the size of this RAB, right? So it will be n space, n log n time construction, and also you should be able to give me the sample in log n time. All right, so this is very easy. In fact, you can even do constant query time. We don't care about polylog, so constant polylog. For today, they are the same, right? But just so you know, you can do constant time, and for construction, you can do linear in expectation as well. Okay. Just to mention a little bit more, this is called the alias structure. Okay, so for those of you that have been attending the series from the beginning, you understand what I'm saying. But the material is on the page of the seminar. Okay, so this is called the alias structure. All right, but you don't need an alias structure if you are willing to go for log n time. Okay, you can just use, for example, tree sampling, binary search tree. That's quite standard. Okay, all right, good. Just so you know, group by sum and group by weighted sampling. All right, so these two are two useful tools in our toolbox now. Okay, and we'll be building such kind of data structures as we go to help ourselves. All right? Okay, good. That is very nice. Okay. All right, so now let's talk about how to computing the joint result size. Okay, so let's copy this. Okay, let's talk about this. All right. So I will identify the core relation, the core problem. Okay, and then I'm going to identify a recursive recurrence, a recursive relation, so that you know that the problem can actually be solved in a recursive manner. Okay, so in general, I have this joint tree, right? This joint tree, this T, as you can see, T is the tree here. Now, let's say E is a node in the tree. Now, remember, this is a hyperedge, right? This is the schema of some relation, okay? So I'm going to use QE to represent the subjoin, okay? We talked about this concept before, subjoin of E, all right? So this is basically saying you look at the relations that are in the subtree of this node, all right? So those relations define this subjoin, all right? So for example, if I say, okay, BG is the node E I am talking about, and then what is the subjoin? Well, you just look at the subtree how many relations do you have in the subtree? You got 6 relations, right? So the subjoin of this no subjoin of this BG is just the original join. Okay, so all right, so that's supposed to be funny. All right. Anyway, so if you look at BE, all right. So this time, if I say what is the subjoin, simple, right? Subjoin, subtree, right? So how many relations are there in the subjoin? 4 this time. Okay. All right. So this one is a little bit, let's say, unconventional, right? So if I say, okay, now let's look at this, EF. What is the subjoin? Well, you can tell me there's no John here. There is, right? It's just that the John has only one relation, but it is a John. You see what I mean? Good. So this is the subjoin. Very nice. Okay, good. Now here is something I want to uh, solve as a subproblem. Okay, so you see this yi, right? And this yi has re. By the way, re is just one relation. Okay, so I mentioned a lot of concepts here. I hope you haven't got them mixed up, right? So this QE is the subjoin, and RE is just one relation in the subjoin, correct? Okay, good. So if I say now let's look at a tuple in this RE. Okay, look at this tuple in this RE. I want to consider the following. Well, I'm going to write out the expression first, and then I'm going to tell you, I'm going to ask you whether it makes sense. Okay, you know what? I'll leave out the size operator first. So if I say I'm interested in this, does it make any sense to you? Okay, so okay, you know what? Let's take it slow, right? So let's say that we're talking about this BG here, and let's just say that this U, is a tuple inside this BG. Okay, so if I say I'm interested in you joining this QBG, okay, does that make sense to you? Now let's take a moment to understand the meaning before I continue, right? Because this is something very natural. Okay, so if you look at this John QBG, right? So that is the John result of the entire subjoin, which is just the entire John, right? However, not all those Johns are relevant to you. You see what I'm saying? Only some of them are produced by you, are generated by you. You see what I'm saying? Now, this is essentially saying, you know what? I want only the part of the John result that is relevant to you. Okay, so basically, you can also say, okay, what are the tuples that are produced by you? Okay, good. So in general, this is the expression. Sorry, this is the meaning of this general generic expression I have there, right? So if you look at this yi can be anywhere. For example, that yi could be be. If you look at the subjoin, the subjoin is this join. If I say I look at a tuple in the relation of be, right, and I want to know, okay, what is the part of the result in this subjoin that are produced by the tuple inside this BE. Okay, so this is the meaning. Okay, now here, this is the problem I want to solve. I want to be able to compute the number of tuples contributed to by this U. Okay, so this is the core problem. So okay, so this is something called the subjoin weight. Okay, subjoin weight. Oh, I'm sorry. I just give me a moment to make this tidier. Subjoin weight. You see what I mean? Okay, now just a quiz, right? So let's say U is BG there. Okay. Now this time I'm going to use the terminology, right? So what is the subjoin weight of U? Well, then you should know this is just a number of tuples in the subjoin of BG, which is the entire join. Okay, that are produced by U. Okay, so if I say, okay, now let's move U to a tuple in here. Okay, so BE, right? So if I say, what is the subjoin weight of U? Okay, you see terminology, right? So you should tell me, okay, now let's look at the subjoin of BE. So this is the subjoin, right? Now let's just extract all those tuples that are produced by you. Okay. By the way, is it possible for the subjoined way to be 0? No. Okay. Why? Because this is fully reduced. All right. So this is fully reduced. This U definitely contributes something to the final join, and therefore definitely to every single subjoin, right? Okay. Now the next question could be a little weird, okay, but it's legal. Okay, now this time let's say Y is just AB. All right, so I'm gonna say what is the subjoin way? By the way, U is a tuple in AB, right? So I'm gonna say so I will ask you, what is the subjoin way of U here? Okay, as I said, right, this might feel a little weird. Uh, it's actually the simplest question I have ever asked because there's only one unique answer, right? You apply the definition, right? So what is subjoin? The subjoin contains just AB itself, right? And then inside the result of this subjoin, by the way, the result of the subjoin is just AB itself, right? Which part is produced by U itself? Well, just U itself, right? So the subjoin way is definitely one. You see what I'm saying? Good. So I can tell you that this is the core of everything. All right. So if you want to count the output size of the entire joint, this is the problem you want to solve. Okay. Why? Because once you are able to solve this problem everywhere, by everywhere, I mean for every single relation. Okay. And then you are able to easily uh, compute the result size of the overall joint. Okay. Why? Because all you have to do is to go back to the root. You see what I'm saying? Okay, you will say U is in the root. Okay, U is a tuple in this root relation, right? And then you will ask the question. Okay, let me indicate. U is in here, right? So I go through every single U, every single tuple in the top relation, right? I would say, okay, for this tuple, now tell me what is your subjoin way. So by definition, this is the number of tuples in the final join result that are relevant to this tuple, correct? And then you move on to the next tuple, da, da, da. So all you have to do is to sum up the subjoin weights of all the tuples in the top relation, and that's it. Okay. So this is the core of the problem. Once I have identified this subproblem for you, and then you can go ahead and think about how to solve it. Okay, so you can already start thinking about it, right? Indeed, this is not going to be difficult now, right? So we will see a bottom-up algorithm, okay? And this bottom-up algorithm allows us to utilize a property, a structural property behind the subjoin weights. And in turn, this property is made possible by the decomposable lemma, decomposability lemma. Okay. All right. So now let's do this analysis. I'm going to show this show you an example, actually with using just this example, and then the idea should be fairly fairly clear. Okay. By the way, as the base case, right? So if this yi is a leaf relation, let's say if I'm talking about AB, U is from AB, or U is from BD, or EF, or GH. This is easy because, as I said, right, the subjoin way is always one in that case, right? So you trivially solve the base case, all right? So if I say build a data structure for it, that's data structure you need, right? Just the relation itself. Now, inductively, okay, inductively, suppose that I have already solved this problem. By the way, yi is now an internal node in the tree, right? So suppose I have already solved this problem for all the child nodes, actually for the entire all the nodes in the proper subtree of yi, right? So now I'm looking at yi itself, right? How do I solve it, right? So that's the problem I'm getting at right now. Okay, so I will explain how to solve this by illustrating an example, but this example is general enough to illustrate the idea. So let's look at BG. All right. Now suppose I have already solved the problem for BE and GH. Okay. So let's see how to solve the problem for BG. Okay. Good. Now you give me a tuple U. I will show you that I can find its subjoin way in basically constant time, ignoring polylogarithmic factor. Okay. So when I say basically constant time, this means big O tilde. Okay, so I'm omitting a polylogarithmic factor here. So why is this possible? Well, let's see, right? So this is something that we can write as follows, right? So you can see this um, this E is BE, right? Okay, good. Now let's work on this part here. Okay, using decomposability, right? So don't forget, this is exactly what the decomposability lemma is about, right? You want to compute this part of the final joint, right? So you want to know, okay, how to do so, right? And you know that at this point you are able to break it into uh, two joints, and then take the Cartesian product of the two joints, right? So so here you can look at it as saying you can look at it as saying, okay, so this is U joining the left part. So the left part is actually a join with four relations, okay? But we have already defined the notion of subjoin, right? So therefore we can conveniently indicate this relation with, this join with four relations by just saying QBE, right? So this is clear, right? So this is the first part, okay? So imagine you take this part, and then there's some sort of a Cartesian product going on, right? And then you have this U join, this GH, okay? So basically, this expression is equivalent. This equivalent is not entirely precise. Why? Because basically the attribute of U would appear twice, right? But anyway, you do the projection, you know that all those attributes, their values will have to be the same on the left hand side and the right hand side, because they are the values of U, right? Anyway, so if you ignore this, this Cartesian product makes sense, right? So if you want the exact statement of the decomposability lemma, last time I talked about it using a procedure, if you still remember it. Okay, anyway. So, however, here we're not talking about the result, the result of these two joints, right? We're only talking about the size. You see what I'm saying? And therefore, because it's a Cartesian product, and then you know that I can simply compute the the size of the left part and the size of the right part, and then taking the product, right? So this will be exactly what I need here, okay? All right, so these two parts, they are essentially symmetric, okay? I will focus on this part, okay? Because this part is actually slightly more complicated because the subtree has more levels, okay? So I will show you how to compute this part, all right? The same idea goes for the right part as well. So now let's focus on this. Let's have this green ripple here. Okay. Now I'm going to work on this part. This part, is equivalent to, I can break it up into the following, right? So look at this U. So I will think about V's in BE that can join with U. You see what I'm saying? Because this BE is a relation participating in the left join here, right? So I ask the question, okay, which tuples in BE are relevant to U? You see what I'm saying? This U and V, they share attribute B. You can see that, right? Share attribute B. And you know that if U and V are relevant to each other, their B values will have to be identical to each other, right? Otherwise, they are irrelevant, right? And therefore, if I want to compute the left-hand side, I don't really need the entire BE. You see what I'm saying? I need only one group. Okay, now the group concept comes out, right? Now this is important, right? I need only one group. Now, which group? The group whose B value is exactly the same as the V value of U, right? Okay, so therefore I can just look at those tuple in RBE. All right, so this tuple, they satisfy the condition that the b value of this v is equivalent to the b value of u. Okay, so I take this tuple, all right, and then I say, okay, I only want the part of the subjoin that's relevant to the tuple. Okay, so you see v is from RBE, and this is the subjoin of RBE, right? Again, what is the meaning of this? The semantics, right? So you look at the subjoin, and then you ask the question, which part of the subjoin is relevant to V, right? You take those tuples out, and then these tuples, and only these tuples, if and only if here, right? So they can join with you. Okay, so this is equivalent, all right? And therefore, if you only care about the size, you can turn this into a summation now, right? So this is the summation, such kind of tuple. Okay, and simply you look at every v, okay, and you ask yourself, okay, in its own subjoin, right? In its own subjoin, how many tuples are relevant to you, right? So you can see this is a strict equivalence. Okay, good. Now you can see the recursion, right? Because what is this part? Well, this is nothing but the subjoin weights of v. Okay, but I told you, right? So I have already computed all these things, right? So now here comes the question, right? So I have this u, right? I have computed the subjoin weights for BE, right? So this is the inductive assumption, right? So how would you be able to build a data structure right now to help yourself? Now, what do I mean by helping yourself? You have all the subjoin weights of the tuples in BE. Now you want to create a data structure so that when I give you a U from here, you are able to compute the sum in constant time. By constant time, I mean logarithmic time. Okay, are you able to do that? The answer is yes. Why? Because this is simply a group by sum problem. You see what I'm saying? Okay, so we were talking about BE here, right? So now what is the weight of each tuple? So the weight is simply the subjoin weight, which you have already computed. Okay, so you do that, and then you build a data structure like this. Now this time I give you a U, and then essentially I'm saying I want one group, right? So from this group, you tell me the group by sum, right? So now you can see the whole algorithm already. Okay, so the algorithm is actually a bottom up, right? So it feels very similar to Yanakaki's algorithm, right? Indeed, I mean, all these algorithms, they are made possible by the decomposability lemma. All right. So basically, you want to process the relations bottom up. You see what I mean? So you want to go with A, B. You want to go with the leaf relations first. So A, B, B, D, E, F, G, H. Basically, for these relations, you don't need to do anything. You see what I'm saying? All right. Now, when you process BE, before you process BE, what you want to do is you want to create a group by sum structure on AB, and then BD and EF, right? So this takes only time linear to the number of tuples in those relations, correct? And then for every V here, for every V in BE, what you can do is to spend just constant time, okay, polylog, okay, constant time to look at, to retrieve a group by sum from AB, okay? But you also have to retrieve a group by sum from BD. You also have to retrieve group by sum from EF. And then you take the product of these three sums, right? Why? Because you have the decomposability lemma to help you, right? So that takes only constant time because you have only three relations. Now remember, the number of relations here is a constant, right? Which is to say that if the number of relations is not a constant, you can easily extend this analysis, to suit your purpose. So you can see I'm making this assumption simply for simplicity here. Okay, good. So, and then you spend constant time for every tuple in BE, and then you are done with BE. You see what I mean? And now you are able to construct a group by sum structure on BE, right? And then you work on BG in the same way. You see what I mean? So overall, this gives you a linear time algorithm. Okay, so this is the algorithm for computing the result size. Okay, all right. Now, if this makes sense to you, going to sampling is just following following the same idea, except that you want to um, replace the group by sum with group by weighted sampling. Okay, so the idea is very uh, uh, similar. Okay, so I'm going to extend. So I will stay on this page. Okay, so I'm going to extend the discussion. Actually, I will modify the writings here, um, just the necessary parts to turn the discussion into sampling. Okay, so remember the goal here is to create a data structure overall. Okay, and then when we're done, we say, okay, now we're ready. And then you can say, hit me, hit me. You see what I'm saying? Whenever you say hit me, and then I have to hit you with a uniform sample from the data structure. Okay. So the pre-processing phase should take up linear time. All right. And then after that, I should give you a sample constant time. Now, this time, this constant is really something that cannot depend on the number of tuples, right? Okay. Um, when I say constant, I mean polylog. Okay, so yeah, I have to be careful. But indeed, it's possible to achieve constant time if you use hashing. Okay. All right. So just like before, let's identify the core problem. Okay. The core problem is this. Okay. Say you look at a relation. Um, in the tree, okay? Just like RE, like what I said before, right? So for example, BG, so U is BG here. And then you say, I take, sorry, the relation is BG. And then I take a tuple U from this relation, okay? And then I worry about the part of the join result that's relevant to me, right? So this is the part that we have been talking about, right? Before we were just calculating its size, but now you want to be able to uh, have a data structure that at any moment can hit you. You see what I mean? Except that by hitting you, I mean I give you this U. Now you are going to give me a uniform sample from the result of this join. You see what I'm saying? All right, good. And you have to be able to do this everywhere. You see what I mean? So for example, if I say, now this time, let's look at BE as the relation, right? So you have to prepare yourself a data structure such that if I give you a V this time, okay, V, and then I say, okay, V, and then look at the subjoin result that's relevant to B, but I don't want all the result. I just want a uniform sample. You have to say, here it is in constant time. Okay, good, very nice. So this is the core problem that we try to solve. And again, we will take a bottom-up approach, right? So let's start with the leaves, right? The leaves are super easy, right? Because same as before, right? So this time, if I say the relation is AB and here is a tuple in AB, okay? So I want a uniform sample relevant to this tuple. And then you say, here it is, you already have it, right? It's just a tuple in your hands. You see what I'm saying? So you don't have to do anything for the leaf relations, right? So inductively, let's assume that the child nodes are done. Okay, the subproblem has been solved, on the children. Okay, and then we will worry about the parent, right? So again, I'm going to use BG to illustrate the idea. Okay, good. Now the same thing applies. You see what I'm saying? The same thing applies. Okay, so this is the Cartesian product theorem, correct? So now you can see because of the Cartesian product nature, you can turn the sampling into two parts. You see what I'm saying? All right, because you can see this is S1, S2, right? So if I say, hey, take a random sampling, take a uniform sample from the Cartesian product between S1 and S2, what are you going to do? You're going to say, okay, so from S1, I take a uniform sample. From S2, I take a uniform sample. I put them together, and here is the uniform sample from the Cartesian product, right? And this is correct, right? You can calculate whether it's correct, or you can calculate the probability for every pair in the Cartesian product to be sampled, right? So it turns out to be correct, right? Good. And therefore, I will focus on the left-hand side, right? So it suffices to explain how to sample from the left-hand side, okay, rather than the right-hand side. Okay, the same idea is there. Okay, good. So I think the idea is already fairly straightforward. So you know that this part is this part holds for sure, right? So this always holds, right? The green part here. And then you already know that you don't really need to look at the entire BE, right? As we discussed before, all you have to do is look at one group inside the BE, right? So which group you want to have, you want to look at the group with the same B value as you, right? Now, there is something you have to worry about. Okay, be careful. So if you look at every group here, now let's look at this BE, right? So let's look at this group, right? So this is the group that I want. Now you have three tuples, but you have to remember these three tuples, they are not equally important. You see what I'm saying? Because each of these three tuples, let's say V1, V2, and V3, right? Each of these tuples, they might have different contributions to the subjoin at BE. You see what I'm saying? All right. And therefore, you think about it, right? So let's say this guy might generate 100 tuples in the subjoin. This guy 50 and this guy 10. You see what I'm saying? All right. So now if you look at this part here, right? So this tuple, right? So this U, right? So if you look at U, right? So V1 is going to produce 100 tuples with U, and V1 is going to produce 50, right? And V3 is going to produce just 10. You see what I'm saying? So when you say I want a uniform sample from here, you are talking about a population of 160. You see what I'm saying? And therefore, if you say I want a uniform sample from here, essentially you have to do a two-level sampling. You see what I'm saying? You have to say, okay, now let's see if I want V1, V2, or V3, and it's not uniform sampling. This is weighted sampling. So that's why you want to perform a weighted sampling first, right? So let's say you get this V1, with probability 100 over 160. Okay, so if this V1 is what you have got, and then you can focus on retrieving another uniform sample from the subjoin result that's relevant to V1. You see what I mean? So basically, you want to get something from this 100 tuple, right? But this is something that has already been solved. You see what I mean? Because we said we are able to do this sampling operation on BE, on every tuple of BE, right? And therefore, this is something that you can do recursively. Okay. So how do we? So now the algorithm should be clear, right? So now you know that in order to support this operation, you want to do the group by weighted sampling. Okay. And this is the other preliminary data structure we have already explained, right? So overall, the idea is this, right? So you want to process the relations bottom up, right? So for A, B, B, D, E, F, G, H, basically you don't have to do anything, right? Now for BE, right? So for BE, before you process BE, right? So you have to build a weighted sampling structure on AB, right? By the way, for this weighted sampling structure on AB, every tuple carries the weight of 1. Okay, so it's not really a problem. Okay, so you want to do this on AB, and you want to do the same thing on BD and EF. Okay, and now for every tuple in V, right? You can do three. You can do three group by weighted sampling. So I mean, you take a tuple from AB, take a tuple from BD, and take a tuple from EF, right? And then you put them together. You see what I'm saying? All right. So after you have already done that, right? You want to build. Okay, I'm sorry. I think I have make some mistakes here. So I'm already talking about how to answer a query, right? So I should go back a little bit. Okay, I should go back a little bit. So I should first talk about data structure, right? So for data structure on AB, all you need to do is to do a group by, to build a group by weighted sampling data structure. Okay. For BE, same thing. All you have to do is to build a group by weighted sampling data structure. But you have to be careful. When you build the data structure, you need the weights. But these are just the subjoin weights. You see what I mean? The subjoin weights have been computed before when we solved the counting problem, right? So in terms of data structure, there's no sampling yet, right? You simply build the group by weighted sampling data structure, right, based on the subjoin weights that you have already computed, right? So you do this for BE, you do this for BG. So that's the data structure. And then sampling. Okay, and then I can go back to what I was talking about, right? So let's say you are already here. Okay, so what you want to do is you want to sample, from AB, from BD and EF, and then basically you put those two, both put those tuples together, right? So starting from the beginning, right? So this is to illustrate the weighted sampling, right? If you want something from here, you say you have a U, and then you should look at the group of BE. You should look at the group of GH. You see what I mean? So from BE, now here you want to do a weighted sampling. Okay, and depending on which one you take, now from there you have a V, and then from this V again you go down. You sample one tuple from A, B, B, D, and EF separately. Okay, so that is the idea. Okay. Okay. All right. So this is everything for today. Okay. So I will